coarse-grained or this coarse-grained basically for the protein structure, we consider the coarse-grained. But when we have to work on protein and ligand, so in the ligand, the atoms will be there, no residues will be there. So we will be working on the molecular dynamics. Here we will briefly understand the steps which are involved in the molecular dynamics simulation. Okay, the very first thing, initial coordinates. As I told you, it is a time dependent process. Okay, over the time, what things are happening, how the system is reacting. So initial coordinates will be, but the coordinates will be initialized basically. Then we will minimize the structure. Why we are minimizing the structure? So that we can release the excess strain from the system. Okay, remember in the docking also we have minimized the structure. Structure minimization is required to release the excess strain so that it will not affect the activity somehow. Okay, during the docking as well as simulation in both cases. Okay, we will assign the initial velocities. Now here we will assigning the initial velocities and then heating the dynamics. Why heating? Because as I told you, we have to mimic the organism's structure or the whatever the behavior. How, for example, the human only we have to work on. So we will raise the temperature so that at which we can, we wish to carry out the simulation. So we wish to carry out the simulation. For that you have to understand for which organism you are working on. For that organism, what is the normal temperature, at what temperature the system works. Okay, that thing, on that basis you have to raise the temperature, raise the pressure, then you have to equilibrate. Okay, before measuring any properties, what is happening to the system, you have to equilibrate the system. Okay, that is the equilibrated dynamics. If the temperature is okay, then go further. If it is not okay, then further go back and equilibrate the dynamic. Equilibration is most important. Okay, production is what? That is the outcome, that is the output file basically, that will tell you how the system has been studied, what happened to your system. Okay, that is what your molecular dynamics. It is a complex procedure. It is not like this structure may not help you to understand what exactly is happening. What are these initial coordinates? Basically, the initial coordinate is nothing but the initial position. Okay, the very initial velocity of the atoms. Okay, that means you are not doing anything. Whatever it is, just let it be. The system will note it down, the initial one. Okay, so at the 0 time step, it is a time dependent process, right? So at the 0th time step, what is happening to the system? Then the time is increasing. You are making the changes, the temperature, the pressure, what is. So the force field, like how this time is moving, how the things are happening, it is further dependent on the force field. Okay, this force field basically, that provide the key contribution to this molecular potential energy. Okay, it is all energy dependent. So can you see, this is your protein. Just imagine this is your protein. This is surrounded by this box. This box is what? Your human body. Okay, this is surrounded by all the things that is in the normal human body or the normal organism. The protein is surrounded by, and how it will work within this system. Whether it will remain bound, whether it will drift away, whether it will somehow being stable. Sometimes what happens, it remain bound, but nothing is happening. The things are not happening. Okay, things are not happening means how we analyze the result of simulation. Basically, the RMSD and RMS are two things basically we majorly consider. RMSD is the root mean square deviation. That means how the structure is deviated from the initial one. Okay, the initial structure you have submitted, after the simulation, how much deviations has been occurred. And the root mean square fluctuation. Fluctuation are what? Fluctuations in the residues. Okay, so for example, we assume the two residues are there which are responsible for the activity. These are the active site residues. If you are finding less fluctuations in the active site residues, that means your compound, your drug is remain bound to the active site residues. That is a good thing. Okay. Okay, this much is for the molecular dynamics simulation. So these are the tools available for the SPDB, structure-based drug designing, for the target modeling. Like if the structure is not available, you want to model it by yourself, you can go for the Swiss model, modeler, iTester. These are the tools basically. For the binding site, if you are modeling the structure, you have to identify the binding site as well. Okay. If the structure is already solved, the binding site will be known. But if the structure is not yet solved, you are modeling it, then you need to go for the binding site or the active site prediction as well. The CAST-P and active site prediction tool, these two are available. Many more are there definitely. For molecular docking, Autodoc, BINA, Glide, Gold, Hex, HAPR, so many things are there. Okay. ADME properties, Swiss ADME is there. Molecular dynamics, GROMACS, Amber, CHARM, many others are available. Okay. Now, whatever the things we have done, we have to see like whatever happened to your protein or the ligand. Here comes the visualization. Whatever things are going on, you need to visualize them. So basically, visualization tools are required at every stage. In the beginning, when you are downloading the data, when you are downloading the mole file of your protein, of your chemical compound, you need to visualize that. Okay. For that, visualization tool is required. For visualization of the protein structure, after docking also you need to visualize it. After simulation also you need to visualize it. So visualization tools are most important thing in the CAD. So there are many more. The PyMol, Discovery Studio, Chimera, PDB, Swiss PDB viewer are small. Many more are there. I will show you one